Hello, in this video we'll be working through Unit 5 homework problems 1 through 12. We want to determine whether Rolles' theorem can be applied to the function on the indicated interval. And if Rolles' theorem can be applied, we want to find all values of c that satisfy the theorem. So in order to determine whether Rolles' theorem can be applied, we need to check three things. First of all, we need to check, is our function continuous? Is f of x continuous on our closed interval? So in this case, 0 to 4. And then number two, we want to check, is f of x differentiable on the open interval 0 to 4. And then finally, we want to know, is the value of the function equal at our endpoints? So is f of 0 equal to f of 4? Okay, so let's talk about this. Is f continuous on the closed interval from 0 to 4? Well, f of x is a polynomial function, and polynomial functions are continuous everywhere for all real numbers. So yes. Is it differentiable? Polynomial functions are differentiable everywhere. So yes. It's a nice thing about working with polynomials. They're continuous and differentiable everywhere. Now, is f of 0 equal to f of 4? That we have to check. So f of 0, we're substituting 0 in for x. We get 0 squared minus 4 times 0, which is 0. And then f of 4, we get 4 squared minus 4 times 4, and that is also equal to 0. So all three conditions are met, and that means Rolles' theorem does apply, and it guarantees that we have some value c between 0 and 4 where the derivative of f is equal to 0. So to find that value, we take the derivative of f prime of x equals 2x minus 4, and we see where does that equal 0. So 2x minus 4 equals 0. To solve this, we're going to factor out a 2. And then we set each factor equal to 0, and we get the solution x equals 2. Then we want to verify, is that value on our interval? Is 2 between 0 and 4? Yes, it is. So that's the c value that we're looking for. C is equal to 2. Number 2, f of x equals x plus 4 squared times x minus 3. Now we're working on the interval from negative 4 to 3. So does Rolles' theorem apply? First of all, is f continuous on the closed interval? Yes. So I'm going to say f of x is continuous on that closed interval from negative 4 to 3. Number 2, f of x is differentiable on the open interval from negative 4 to 3, and I know this because f of x is a polynomial, and polynomials are continuous and differentiable everywhere. And then number 3, we're going to check at our endpoints, is the value of the function equal? So f of negative 4 is negative 4 plus 4 squared times negative 4 minus 3. That's equal to 0. Oh, not number 4, we're just checking the other endpoint. So f of 3 equals 3 plus 4 squared times 3 minus 3. That is equal to 0. So we have f of negative 4 equals f of 3. So all three conditions have been satisfied. So Rolles' theorem does apply, and we can find some value c between negative 4 and 3 where the derivative is equal to 0. So derivative requires use of the product rule. So we're going to take the derivative of the first factor, which is 2 times x plus 4, multiply that by the second factor, plus the first factor times the derivative of the second factor, which is just 1. Now we want to know, where does this equal 0? So I'm going to do some simplifying first. Ideally, I want this to be in factored form so I can solve it more easily. So each one of these terms has x plus 4 as a factor. I'm going to factor out an x plus 4. So here I'm factoring out this x plus 4, and here I'm factoring out one of the x plus 4s. So that's leaving behind 2 times x minus 3 from the first term and x plus 4 from the second term. And then I'll simplify in the brackets here. So that's 2x minus 6 plus x plus 4. And here we have 2x plus x, that's 3x, minus 6 plus 4 is minus 2. Okay, so now we want to set our derivative equal to 0. And this is going to equal 0 when x equals negative 4 or when x equals positive 2 over 3. So it looks like we have two solutions. But remember, the theorem guarantees our solution will be in our interval. So we want the solution that's between negative 4 and 3. So 2/3 is between negative 4 and 3. That's the value of c that we're looking for. Number 3, f of x equals 4 minus the absolute value of x minus 2. We're working on the interval from negative 3 to 7. So does Rolles theorem apply in this case? Well, this is not a polynomial function. So in order to determine if it's continuous and differentiable, it's really helpful to try and visualize the graph. The parent absolute value function, just f of x equals absolute value of x, looks like this. It has its vertex at 0, 0. It's got a slope of 1 on the right, negative 1 on the left. So if we think about the graph of our function f of x in terms of transformations, this is shifted 2 units to the right. Okay, so our vertex is no longer at the origin. It's shifted 2 units to the right. It's shifted 4 units up. And then it's reflected across the x-axis. And that reflection happens before the vertical shift. So we end up with a graph that looks something like this. And we have a corner point when x is 2. And this function f of x is therefore not differentiable at x equals 2. X equals 2 is in our interval, and so we have failed to satisfy all of the conditions for Rolles' theorem. So we'll say since f of x is not differentiable on the interval from negative 3 to 7, Rolles' theorem does not apply. So our function is continuous on the closed interval, but it's not differentiable on the open interval. So we are not guaranteed that somewhere between negative 3 and 7, the derivative will equal 0. And if you look at the graph, we can see actually that that's not true. There is no point between negative 3 and 7 where f prime will equal 0. Number 4, f of x equals sine x, and we're working on the interval from 0 to 2 pi. So if you think about the graph of sine x, that graph is smooth and continuous and differentiable everywhere. So right away we've satisfied the first two conditions. So we can say f of x is continuous on that closed interval from 0 to 2 pi. You could also say it's continuous from negative infinity to infinity, but we don't need it to be continuous everywhere. We just need it to be continuous on our closed interval from 0 to 2 pi. F of x is differentiable on the open interval from 0 to 2 pi, and it's actually differentiable on the closed interval, but again, we don't need it to be differentiable on the closed interval, we just need it to be differentiable on the open interval. So in this particular case, it would be okay if we combined steps 1 and 2 and said that it's continuous and differentiable on the closed interval from 0 to 2 pi. Or even if we said continuous and differentiable over the set of real numbers. Number 3, we want to check our endpoints. F of 0 equals the sine of 0, which equals 0. And then f of 2 pi equals the sine of 2 pi, which equals 0. So we have f of 0 equals f of 2 pi. Now, coincidentally, in all the problems we've looked at so far, the value of the function at the endpoints is equal to 0. And that doesn't have to be the case. It would be okay if f of 0 was, 0.6, as long as the other endpoint also had a function value of 0.6. They just have to be equal to each other, but they don't have to equal 0. So we have satisfied all three conditions, therefore Rolles' theorem does apply, and we know that there will be a solution somewhere between 0 and 2 pi where the derivative is equal to 0. So let's find that value. F prime of x equals cosine x. That was simple. And then we set our derivative equal to 0, so cosine x equals 0, and solve. Cosine x is equal to 0 on the interval from 0 to 2 pi when x equals pi over 2, or when x equals 3 pi over 2. Now we're only going to keep the values that are in our interval, but both of these values are in our interval. So both of these are solutions guaranteed by our theorem. So we'll say c equals pi over 2 and 3 pi over 2. Now there are other places where the derivative is 0, but remember we're just working on the given interval, 0 to 2 pi. Number 5, f of x equals cosine of 2x. So the graph of cosine 2x, this is a sinusoidal function. It's smooth, continuous, differentiable everywhere. So we know that it is continuous on our closed interval. And we know that it's differentiable on our open interval. And again, in this particular example, since it is continuous and differentiable everywhere, it would be okay if we combine these two steps together and said f is continuous and differentiable on the closed interval. And then we want to check our endpoints. So f of pi over 3 is the cosine of 2 times pi over 3. Cosine of pi over 3 is 1/2. Cosine of 2 pi over 3 is 1/2, but we're in quadrant 2, so it's negative 1/2. Our other endpoint, we want f of 2 pi over 3. So that's the cosine of 2 times 2 pi over 3, or 4 pi over 3. So our reference angle is pi over 3. Cosine of pi over 3 is 1/2, but 4 pi over 3 is in quadrant 3, and here the cosine is negative, so negative 1/2. The value of the function at each of these endpoints is the same, so we have f of pi over 3 equals f of 2 pi over 3. Good, so I'm glad we finally see an example where they're not both equal to 0, because again, they don't have to be equal to 0, they just have to be equal to each other. So we've satisfied those conditions, and now we can find the value of c by letting our derivative equal to 0 and solving. So f prime of x equals the derivative of cosine 2x. We need chain rule to take this derivative. The derivative of cosine stuff is negative sine stuff times the derivative of the stuff. So negative sine 2x times the derivative of 2x, or negative 2 sine 2x. Now we're going to set our derivative equal to 0 and solve. We can divide both sides by negative 2. We get sine of 2x equals 0. Where does the sine equal 0? Well, in general, sine equals 0 at 0, and pi, and 2 pi, and 3 pi, and 4 pi, etc. So our angle 2x is going to be equal to 0 plus multiples of pi. And now solving for x, that means x is equal to 0 divided by 2 is still 0, plus pi divided by 2 times k. So we have to only keep solutions that are in our interval. So multiples of pi over 2 that are in our interval. Our interval goes from pi over 3, which is here, to 2 pi over 3, which is here. So we're only working with this interval, and the only multiple of pi over 2 in that interval is pi over 2. So we have c equals pi over 2. For this next set of problems, we're working with the mean value theorem. So Rolles' theorem is a special case of the mean value theorem. In general, the mean value theorem, if the conditions are satisfied, guarantees that somewhere the derivative will equal the average rate of change on our interval. Not necessarily that the derivative will equal 0, just that it'll equal the average rate of change. So the conditions for the mean value theorem are just that we are working on with a function that is continuous on our closed interval and differentiable on the open interval. We do not need the function values to be equal at the endpoints. For number 6, our function is x cubed minus x squared minus 2x. This is a polynomial function, so it is continuous and differentiable everywhere. So we only have 2 conditions to check for mean value theorem. F of x is continuous on our closed interval from -1 to 1. And then f of x is differentiable on our open interval, -1 to 1. Okay, so both of these things are true, so the mean value theorem does apply. We need to find our derivative, f prime of x, and we need to find the average rate of change on this interval, and then we'll set those equal to each other and solve. So let's start with our derivative. F prime of x equals 3x squared minus 2x minus 2. Okay, and then our average rate of change equals f of 1 minus f of -1 over 1 minus -1. So this is the f of b minus f of a over b minus a. F of 1 is 1 minus 1 minus 2, so -2, minus f of -1, that's -1 minus 1 plus 2, over 1 minus -1 is 2. So we have 1 minus 1 minus 2, -2 minus 0 over 2 equals -1. That's our average rate of change. Average rate of change is -1. So now we want to know, where does our derivative equal that average rate of change? So we'll let 3x squared minus 2x minus 2 equal -1 and solve from here. So to solve from here, we want to let one side equal 0. I'm going to add 1 to both sides of my equation. I get 3x squared minus 2x. When I add the 1 to the -2, I get -1, and on the right I get 0. So now we want to factor the left-hand side. The only way to get 3x squared is going to be 3x times x, and the only way to get a -1 is a 1 times 1. And we need one of these to be positive, one of them to be negative. So to get a -2x in the middle, it needs to look like that. So that gives us solutions at x equals -1/3 and x equals 1. Now these both could be values that are guaranteed by the theorem, but we want to make sure they're in the interval that we're working on. We're working from -1 to 1, so we're going to use the -1/3. C equals -1/3. Since that's the one that's between -1 and 1. Number 7, f of x equals the square root of x minus 3. We're working on the interval from 3 to 7. This one's not a polynomial function, so we should think about what the graph looks like to determine if it's continuous and differentiable on our interval. So here we have the parent square root function shifted 3 units to the right. So f of x looks like this. Is it continuous on the closed interval from 3 to 7? Yes, it is. Is it differentiable on the open interval from 3 to 7? Well, it's not differentiable at 3. because 3 is an end point and there's nothing to the left of that. But we don't need it to be differentiable at the end point. We need it to be differentiable on our open interval, which it is. Another way you can verify whether a graph is differentiable or whether a function is differentiable if you don't know what the graph looks like, so we could actually find the derivative. F prime of x equals, so we would use chain rule here. This is in the form of square root of stuff, so the derivative is 1 over 2 square root stuff times the derivative of the stuff, which in this case is just a 1. And then this function is differentiable everywhere except where the denominator is 0, and that would be when x is 3. So this function is differentiable, or f of x is differentiable everywhere except at x equals 3. And again, we don't need it to be differentiable at 3. So condition 1, f of x is continuous on the closed interval 3 to 7, and f of x is differentiable on the open interval from 3 to 7. So the mean value theorem does apply here. So we want to find our derivative f of x, which we've done, and we want to find our average rate of change and then see where they're equal to each other. So the average rate of change on the interval from 3 to 7 is going to be f of 7 minus f of 3 over 7 minus 3. F of 7 is the square root of 4 minus f of 3, that's the square root of 0, over 7 minus 3 is 4. So we get 2 over 4, or 1/2. The average rate of change on this interval is 1/2. So now we want to know, where does 1 over 2 times the square root of x minus 3 equal 1/2? Okay, I'm going to cross multiply here. So I get 2 equals 2 times the square root of x minus 3. We can divide both sides by 2. We get 1 equals the square root of x minus 3. We can square both sides. We get 1 equals x minus 3. We can add 3 to both sides, and we get x equals 4. And then let's verify that that solution is in our interval. 4 is between 3 and 7, so that's the C value guaranteed by the mean value theorem. Number 8, f of x equals x plus 2 over x on the interval from 1/2 to 2. This is not a polynomial function, so we want to think about the graph, or it's a rational function, so we know that a rational function will not be continuous wherever the denominator is 0. So in this case, not continuous at x equals 0, but otherwise it is continuous. It's continuous everywhere except for 0. So is 0 in our interval? No, because our interval starts at 1/2 and ends at 2. So on our interval, this function is continuous. F of x is continuous. It's continuous everywhere except 0, but we only need it to be continuous on our closed interval, so I'm going to write that. And it's differentiable on our open interval. And again, if you're not sure about the differentiability part, you can go ahead and find the derivative and then look at your derivative equation and see where does that not exist. And that would be where it's not differentiable. Let's go ahead and find our derivative. So I've got f prime of x equals, I'm going to use the quotient rule. Now I have a choice here. I could simplify f of x and make it 1 plus 2 over x, and then I wouldn't need to use the quotient rule, but this one doesn't look too intimidating. Let's just go for quotient rule. So derivative of the top is 1 times the bottom minus the top times the derivative of the bottom over the bottom squared. And if we simplify that, x minus 2, we get negative 2 over x squared. So this derivative function does not exist when x is 0, but otherwise it does. So it is differentiable on the interval from 1/2 to 2. So the mean value theorem does apply on this interval, and we want to know where does this derivative equal the average rate of change. So our average rate of change on the interval from 1/2 to 2 equals f of 2 minus f of 1/2 over 2 minus 1/2. F of 2 is 2 plus 2 over 2, which is 2, minus f of 1/2. That's 1/2 plus 2 over 1/2. 1/2 plus 2 over 1/2. Over 2 minus 1/2. So 2 minus 1/2 is 3/2. Now there's a couple different ways we can proceed to simplify this. If we want to just kind of work with this here first and simplify that, 1/2 plus 2, 2.5 is 5 over 2. So I have 5 over 2 divided by 1 over 2. When you're dividing fractions with the same denominator, your denominators are just going to end up canceling out. So this is going to simplify to just 5. Or you can multiply by the reciprocal of the bottom fraction. Again, the 2's will cancel out and you're just left with 5. So this is 2 minus 5 over 3 over 2, which is -3. Dividing by 3 over 2 is the same as multiplying by 2 over 3. So now this simplifies to just -2. The average rate of change is -2. So now we want to know, where does our derivative equal the average rate of change? So we set -2 over x squared equal to -2. I can multiply both sides by x squared. So -2 equals -2x squared. Divide both sides by -2, I get 1 equals x squared. And then take the square root of both sides, I get x equals plus or minus 1. But remember, we're restricted to the interval from 1/2 to 2. -1 is not inside of our interval, so we're not going to include that as a c value guaranteed by our theorem. We're just going to use the positive one. So c equals 1. Number 9, h equals 2 cosine x plus the cosine of 2x, and we're working on the interval from 0 to pi. This is a calculator active problem, so we can graph this function to determine whether it's continuous and differentiable, although I can see that it is a trigonometric function, so there are no values of x that are going to make this not be continuous. On the interval from 0 to pi, our function looks something like that. So it is continuous and differentiable everywhere on that interval. H of x is continuous on the closed interval from 0 to pi, and it is differentiable on the open interval from 0 to pi. So the mean value theorem does apply here. Our derivative, h prime of x, equals, the derivative of 2 cosine x is -2 sine x, plus the derivative of cosine 2x is -2 sine 2x. To find our average rate of change on the interval from 0 to pi, we're looking for h of pi minus h of 0 over pi minus 0. So h of pi, we need 2 times the cosine of pi, that's -2, plus the cosine of 2 pi, cosine of 2 pi is 1. Okay, so that's h of pi, minus h of 0. 2 times the cosine of 0 is 2, plus the cosine of 2 times 0, that's 1, over pi. So we have -1 minus 3, so -4, over pi. That's our average rate of change. So now we want to know, where does our derivative, where does -2 sine x minus 2 sine 2x equal -4 over pi? And if we solve that graphically, we can graph the left-hand side, and on our interval that looks something like so. And then we graph the right-hand side. So negative 4 over pi is about here. So we have two solutions on our interval. These values are approximately 0.217 and 1.748. Both of these are on our interval between 0 and pi. So these are both values of c guaranteed by the theorem. For our last set of problems, we're going to use the graph of the function f of x to determine if Rolle's theorem or the mean value theorem, whichever is indicated, can be applied or not. Number 10 is asking if we can use Rolle's theorem on the interval from negative 5 to negative 1. So negative 5 is here to negative 1 right here. So Rolle's theorem requires that the function be continuous on the interval, which it is not. We have a discontinuity at negative 3, and that's in the interval between negative 5 and negative 1. So right away we know we cannot use Rolle's theorem. We also need the function to be differentiable between negative 5 and negative 1, and it's not differentiable at negative 3. If it's not continuous, it's not differentiable. We also need the endpoint values of the function to be equal. So at negative 5 and at negative 1, we do have the same y value. So that third condition is okay, but we've failed to satisfy those first two conditions. So for number 10, no. Our function f of x is neither continuous nor differentiable. On the interval negative 5 to negative 1. Number 11 is Rolle's theorem applicable on the interval from negative 2 to 8. So here's negative 2, or negative 2 to positive 8. Here's positive 8. Okay, so we have from negative 2 to positive 8, our function is continuous. However, it's not differentiable because of this cusp or corner point right here at negative 1. So no, f is not differentiable on the open interval negative 2 to 8. And number 12, does the mean value theorem apply on the interval from negative 1 to 8? So negative 1 right here to positive 8 right here. Okay, the function is continuous on the interval. It is differentiable on the open interval. It's not differentiable at negative 1, but we don't need it to be differentiable at the endpoint. So yes, for a mean value theorem, those are the only two conditions that need to be true. So yes, the mean value theorem does apply. Yes, since f of x is continuous on the closed interval from negative 1 to 8 and differentiable on the open interval from negative 1 to 8. The mean value theorem does apply.